What if I told you that there are places in space where time doesn't exist, where black holes dance with each other and planets rain glass? Welcome to the most mind-blowing hour of your life as we dive deep into the mysteries of the cosmos. Ever wondered what secrets lie hidden behind the vast curtain of space, or how the universe can be more bizarre and astonishing than any sci-fi movie you've ever seen? Stay with us until the end of this video as we unravel the most intriguing, baffling, and jaw-dropping enigmas that space has to offer. Get ready to have your perception of reality challenged and your curiosity ignited. The first mystery we are going to unravel today is about mind-bending black holes. These cosmic giants are known for their immense gravitational pull, which is so powerful that not even light can escape once it gets too close. But what happens inside these enigmatic entities? The truth is, no one knows for sure. Some theories suggest that black holes could be gateways to other parts of the universe or even other dimensions. Imagine a portal where entering one side could spit you out on the opposite end of the galaxy or in an entirely different universe. Then there's the concept of the singularity, a point at the very heart of the black hole where gravity is infinite and space and time cease to exist as we know them. It's a place where the known laws of physics break down and we venture into the realms of theoretical physics. What if these singularities are the birthplaces of new universes, giving rise to a multiverse? And then there's Hawking radiation, proposed by Stephen Hawking, suggesting that black holes can emit particles and slowly evaporate over time. This radiation challenges our understanding of black holes' permanence, adding another layer of intrigue. The mysteries surrounding black holes continue to baffle scientists and ignite our imaginations, serving as a reminder of how much we have yet to learn about the universe. The next enigma that we need to unravel is the mystery of dark matter. Unlike stars and planets, dark matter doesn't emit, absorb, or reflect light, making it invisible and incredibly hard to detect. Yet its presence is crucial. Scientists believe that dark matter makes up about 27% of the universe. So, what exactly is dark matter? Imagine it as an invisible scaffold holding the universe together. Without it, galaxies would fly apart due to their own rotational speed. We can infer its presence through its gravitational effects on visible matter. For instance, when scientists observe the rotation of galaxies, they notice that stars on the outer edges are moving faster than they should based on the amount of visible matter alone. This discrepancy points to an unseen mass dark matter exerting additional gravitational pull. Despite its importance, we still don't know what dark matter is made of. One theory proposes that dark matter consists of exotic particles that we haven't detected yet. Another suggests it might be composed of primordial black holes formed in the early universe. The quest to detect dark matter has led to the construction of highly sensitive detectors buried deep underground, in hopes of capturing the rare interactions between dark matter particles and regular matter. Large Hadron Collider experiments also try to create conditions that might allow us to observe dark matter indirectly. However, despite these efforts, dark matter remains elusive. Understanding dark matter could unlock fundamental secrets about the universe's structure and evolution. It challenges our grasp of physics and encourages us to look beyond what is visible. The hunt for dark matter continues to be one of the most tantalizing pursuits in modern science, pushing the boundaries of our knowledge and imagination. The next mind-boggling mystery we're going to explore is the weirdness of neutron stars. Neutron stars are quite literally stellar remnants with some of the most extreme characteristics known in the cosmos. Imagine a star that has collapsed under its own gravity to the point where protons and electrons have fused to form neutrons, leading to a sphere only about 20 kilometers in diameter, yet packing a mass greater than that of our Sun. This incredible density means that a sugar cube-sized portion of a neutron star would weigh more than 1 billion tons. Neutron stars also possess incredibly strong magnetic fields, which can be 1,000,000,000 times stronger than Earth's magnetic field. These magnetic fields can accelerate particles to near light speeds, creating beams of radiation that sweep across space. When these beams point toward Earth, we detect them as pulsars, delivering precise, clock-like signals that have fascinated astronomers for decades. Another bizarre feature is the crust of a neutron star, which is thought to be the strongest material in the universe. Known as nuclear pasta due to its strange shapes, this crust can support immense stresses. Beneath this crust lies an ocean of superfluid neutrons, allowing the star to spin at astonishing rates, sometimes hundreds of times per second. But perhaps the strangest aspect is the potential presence of quark matter at the core. In this state, neutrons might dissolve into their constituent quarks, creating a form of matter that we can only theorize about. This exotic matter challenges our understanding of particle physics and could provide insights into the early universe. The more we study neutron stars, the more we realize how they defy conventional physics, embodying the universe's ability to surprise and mystify us. Each discovery about these dense, magnetic, and rapidly spinning remnants pushes the boundaries of our knowledge, reminding us of the extraordinary phenomena that lie beyond our planet. The next unfathomable space mystery we are going to delve into is the enigma of fast radio bursts. Fast radio bursts, or FRB, are incredibly brief but powerful bursts of radio waves that last only a few milliseconds. Despite their fleeting nature, they emit more energy in those milliseconds than the sun does in an entire day. The mystery surrounding FRBs lies in their unknown origins and what they could potentially reveal about the cosmos. This phenomenon was first discovered in 2007, and since then, scientists have been baffled by their sudden, unpredictable appearance. These bursts seem to originate from billions of light years away, indicating they are coming from some of the most distant and ancient regions of the universe. One of the most compelling aspects of FRBs is that their sources are not fully understood. While several theories have been proposed, ranging from highly magnetized neutron stars known as magnetas to cataclysmic events like supernova or the merging of black holes, none have been definitively proven. Some even speculate they could be signals from advanced extraterrestrial civilizations, although this remains highly controversial and unproven. What makes FRBs even more intriguing is the discovery of repeating fast radio bursts. Most FRBs have been one-off events, but a few sources have been observed to emit multiple bursts over time. This repetition suggests a non-cataclysmic origin, potentially linked to the behavior of some celestial objects rather than a single explosive event. The study of fast radio bursts has opened a new window into the high-energy processes occurring in the universe, and they are providing insights into the distribution of matter across the cosmos. By analyzing the way FRBs travel through space, scientists can learn about the intergalactic medium they traverse, shedding light on the density and structure of the universe. In summary, the mystery of fast radio bursts challenges our understanding of astrophysical phenomena and the universe's deepest secrets. As we continue to detect and study these enigmatic signals, we may one day unravel their origins and in the process uncover new and profound insights about the universe. Our next cosmic enigma takes us to a mysterious region of space known as the Great Attractor. Imagine a gravitational force so immense that it is pulling entire galaxies, including our own Milky Way, towards it. Despite its colossal influence, the exact nature of the Great Attractor remains largely unknown. Situated about 250 million light-years away in the direction of the constellation Centaurus, this region has puzzled astronomers since its discovery in the 1970s. The Great Attractor's pull is so powerful that it affects the motion of galaxies over a span of hundreds of millions of light-years. This mysterious force gives us a glimpse into the hidden structures and forces that govern the universe. So, what could possibly be creating this enormous gravitational pull? One theory suggests that the Great Attractor could be a supercluster of galaxies, a massive concentration of matter that exerts a gravitational force on a grand scale. However, what makes this more intriguing is that the Great Attractor lies in a region of space known as the Zone of Avoidance. This area is heavily obscured by the Milky Way's plane, filled with stars and cosmic dust, making it difficult for us to observe it directly in visible light. To study the Great Attractor, astronomers rely on X-ray and radio wave observations, attempting to peer through the cosmic veil that hides this enigmatic region. Another compelling possibility is that the Great Attractor could be part of an even larger structure known as the Laniakea supercluster, of which our Milky Way is a part. This supercluster is a vast collection of galaxies spanning over 500 million light-years, and the Great Attractor may be its gravitational focal point. The discovery of Laniakea has provided a new perspective on our place in the cosmos, showing that we are part of a much larger and interconnected web of galaxies. Despite these theories, the true nature of the Great Attractor remains one of the most tantalizing mysteries in astrophysics. It challenges our understanding of cosmic structures and forces us to rethink how galaxies form and move on a universal scale. As our technology and observational techniques continue to improve, we may one day unveil the secrets of this cosmic magnet, bringing us closer to comprehending the vast and intricate tapestry of the universe. The next unsolved riddle of the cosmos is the enigma of dark energy. Dark energy is a mysterious force believed to be causing the accelerating expansion of the universe. Unlike dark matter, which exerts gravitational pull, dark energy seems to do the exact opposite. It pushes matter apart. Imagine an unknown force that is not just preventing the universe from collapsing due to gravity, but is causing it to continually expand at an ever-increasing rate. This concept was first proposed to explain observations made in the late 1990s, where distant supernovae appeared dimmer than expected, suggesting they were farther away than previously believed. This was a clear indication that the universe's expansion was accelerating, not slowing down. So, what exactly is dark energy? The truth is, we don't really know. It makes up about 68% of the universe, yet its nature remains one of the biggest mysteries in modern physics. Some theories propose that dark energy is a property of space itself. As space expands, new space comes into existence, and with it, more dark energy. This idea ties into Einstein's cosmological constant, a term he initially included in his equations for general relativity, but later discarded as his biggest blunder. However, the discovery of the universe's accelerated expansion has revived the relevance of this constant, suggesting that it could represent the energy density of empty space. Another theory suggests that dark energy could be a dynamic field known as quintessence, which changes over time. Unlike the cosmological constant, quintessence would have its own properties and could vary in strength throughout the universe. This dynamic nature would mean that dark energy isn't a fixed value but fluctuates, influencing the rate of expansion accordingly. Despite these intriguing theories, dark energy's true nature remains elusive. Its detection is challenging because it doesn't interact with light or ordinary matter in any detectable way, making it invisible and undetectable by traditional means. Researchers are employing various techniques to better understand dark energy. Observations of the cosmic microwave background radiation, large-scale galaxy surveys, and measurements of distant supernova all provide indirect evidence of dark energy's effects. These observations help scientists create models and simulations to study its influence on the universe's structure and evolution. Understanding dark energy is crucial as it not only shapes the fate of the universe but also challenges our current understanding of fundamental physics. It raises profound questions about the nature of space, time, and the underlying forces that govern the cosmos. The quest to unlock the secrets of dark energy continues to inspire and perplex scientists, pushing the boundaries of our knowledge and imagination. In summary, dark energy is the unsolved riddle that drives the accelerating expansion of the universe. Its mysterious nature and profound implications make it one of the most captivating subjects in cosmology. As we delve deeper into this enigma, we edge closer to uncovering the fundamental truths about the universe and our place within it. The Fermi paradox presents one of the most intriguing questions in the search for extraterrestrial intelligence. In a universe as vast and ancient as ours, why haven't we encountered other intelligent life forms? Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox highlights the contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for or contact with such civilizations. Considering the sheer number of stars in the Milky Way galaxy alone, each potentially hosting planets in their habitable zones, one would expect the cosmos to be teeming with life. Yet, despite decades of searching, we haven't detected any signs of extraterrestrial intelligence. One possible explanation is that intelligent civilizations may be exceedingly rare. While simple life forms like bacteria might be common, the leap to complex, intelligent life could be an extraordinarily rare event. Perhaps the conditions required for such life are so specific that they seldom occur. Another intriguing idea is the Great Filter hypothesis. This theory suggests that there is a stage in the evolution of life that is incredibly difficult to surpass, acting as a barrier that prevents most species from becoming advanced enough to explore the cosmos. This great filter could lie behind us, meaning the development of intelligent life is a rare fluke, or ahead of us, indicating that advanced civilizations tend to self-destruct before achieving interstellar travel. There's also the possibility that extraterrestrial civilizations are deliberately avoiding contact with us. Known as the zoo hypothesis, this idea posits that advanced civilizations might be observing us from afar, much like how we study animals in a zoo and choose not to interfere with our natural development. Alternatively, they might be using technologies and communication methods that are beyond our current understanding, rendering our attempts to detect them futile. We can't rule out the notion that intelligent civilizations are simply too distant to contact. The vast distances between stars mean that even if there are advanced civilizations out there, the signals they send may take thousands or millions of years to reach us and vice versa. Our brief window of modern technology might not coincide with their periods of activity. Another facet of the Fermi paradox is the possibility that extraterrestrial life exists in forms we cannot recognize or don't inhabit planets similar to Earth. They might thrive in environments radically different from what we consider habitable, or they could exist as non-biological entities, such as advanced artificial intelligences that have transcended biological limitations. As we continue to explore and push the boundaries of our knowledge, the Fermi paradox remains an open question. It challenges us to rethink our assumptions about life, intelligence, and our place in the universe. The search for extraterrestrial intelligence is not just about finding aliens. It's about understanding the conditions that foster life and the future of our own civilization. Each step forward in this search brings us closer to answering some of the most profound questions about existence itself. The next fascinating topic we'll explore is the wonders of exoplanets. Exoplanets are planets that orbit stars outside our solar system, and they have captured the imagination of scientists and space enthusiasts alike. What makes exoplanets so intriguing is their sheer diversity, with each discovery offering unique characteristics and mysteries. One of the most famous exoplanets is Kepler 186f, which orbits a red dwarf star about 500 light-years away from Earth. What makes Kepler 186f remarkable is that it resides in its star's habitable zone, a region where conditions might be right for liquid water to exist. This raises the exciting possibility that Kepler 186f could support life as we know it, but the mystery doesn't stop there. The planet's size and composition suggest it could be rocky, like Earth, but we don't yet know what its atmosphere is like, leaving much to the imagination about what kind of world it truly is. Another captivating exoplanet is HD 189733b, located 64 light-years away in the constellation Vulpecula. This exoplanet is a gas giant, but what sets it apart is its incredibly harsh weather conditions. HD 189733b's atmosphere is filled with silicate particles, resulting in glass rain that whips around the planet at speeds of up to 400 miles per hour. This bizarre weather phenomenon gives us a glimpse of how different and extreme conditions can be on distant worlds. Then there's TRAPPIST-1e, one of 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1 about 40 light-years away. TRAPPIST-1e is particularly intriguing because it lies within the habitable zone of its star, and initial studies suggest it could have a stable, temperate climate. The TRAPPIST-1 system is unique because all 7 planets are tightly packed and gravitationally linked, which means they can influence each other's orbits and conditions. This intricate dance of planets provides a natural laboratory for studying planetary formation and habitability. Another exoplanet that boggles the mind is WASP-12b, found 400 light-years away in the constellation Auriga. WASP-12b is a hot Jupiter, a type of gas giant that orbits very close to its star. The intense heat from the star causes temperatures on WASP-12b to soar to over 4000 degrees Fahrenheit. What makes WASP-12b even more mysterious is that it appears to be absorbing rather than reflecting most of the starlight that hits it, making it one of the darkest known planets. This unusual feature suggests that its atmosphere might contain exotic elements or compounds, providing a puzzle for scientists to solve. Then there's Gliese 1214b, also known as GJ 1214b, a super-Earth orbiting a red dwarf star about 48 light-years away. This exoplanet is larger than Earth but smaller than Neptune, and it has a thick atmosphere that may consist of water vapor or an exotic form of ice. The mystery of Gliese 1214b lies in its atmospheric composition and whether it harbors an ocean beneath its clouds. This exoplanet challenges our understanding of planetary atmospheres and the potential for water worlds. And finally, we have Proxima Centauri b, which orbits the closest star to our Sun, Proxima Centauri, just 24 light-years away. This exoplanet is similar in size to Earth and lies within the habitable zone of its star, making it one of the most promising candidates for finding life beyond our solar system. However, Proxima Centauri is a red dwarf star that emits powerful stellar flares, which could strip away the planet's atmosphere. The mystery of Proxima Centauri b lies in whether it has retained an atmosphere and if it could support life despite its star's volatile nature. In summary, the wonders of exoplanets reveal the incredible diversity and complexity of worlds beyond our solar system. These intriguing discoveries challenge our understanding of planetary science and open up new possibilities for the existence of life elsewhere in the universe. As technology advances and our ability to study these distant worlds improves, we move closer to unraveling the mysteries they hold and expanding our knowledge of the cosmos. The next captivating mystery we are going to investigate is the enigmatic WOW signal. Detected by astronomer Jerry Amon on August 15, 1977, this unexplained radio signal has fascinated and puzzled scientists for decades. The WOW signal was picked up by the Big Ear radio telescope at Ohio State University while it was scanning the skies for potential signs of extraterrestrial communication. What makes this signal so remarkable is its intensity and duration. It lasted for a full 72 seconds and was significantly stronger than the background noise, standing out so clearly that Amon circled it on the computer printout and wrote, "Wow." Beside it, giving the signal its famous name. So, what exactly was the WOW signal? the signal came from the direction of the constellation Sagittarius near the Chi Sagittarii star group. However, efforts to pinpoint its exact origin have been unsuccessful. The signal's frequency of 1420 MHz is particularly interesting because it corresponds to the hydrogen line, a universal constant often considered a promising frequency for interstellar communication. Hydrogen is the most abundant element in the universe, and the idea is that an intelligent extraterrestrial civilization might use this natural frequency to send signals across the cosmos. Despite numerous attempts to detect the WOW signal again, it has never been observed since. This has left scientists scratching their heads and speculating about its origin. Was it a one-time transmission from an advanced alien civilization, a natural cosmic phenomenon, or simply an Earth-based interference that went undetected? The absence of a repeat detection complicates efforts to understand the signal, but it has fueled ongoing debates and research into the possibility of extraterrestrial communication. One of the most tantalizing implications of the WOW signal is that it suggests we might not be alone in the universe. If it was indeed a signal from extraterrestrials, it would be the first direct evidence of intelligent life beyond Earth. This prospect has driven scientists to continue searching for similar signals and to refine their methods for distinguishing between potential extraterrestrial communications and terrestrial interference. To this day, the WOW signal remains one of the most compelling and mysterious pieces of evidence in the search for extraterrestrial intelligence. It reminds us of the vastness of the universe and the potential for unknown civilizations to reach out across the stars. Whether we will ever decode the true nature of the WOW signal remains an open question, but it continues to inspire our quest to understand the cosmos and our place within it. The mystery of the WOW signal is a testament to the excitement and intrigue that drives scientific exploration, urging us to keep listening and keep searching, for we never know what extraordinary discoveries await us in the expanse of space. The next enigmatic phenomenon we need to unravel is the mystery of cosmic rays. Cosmic rays are high-energy particles that originate from outer space and travel through the universe at nearly the speed of light. These particles consist primarily of protons and atomic nuclei and have fascinated scientists ever since their discovery due to their immense energy and unknown origins. While we have some understanding of what cosmic rays are, their exact sources and the mechanisms by which they are accelerated to such high energies remain largely mysterious. One of the most intriguing aspects of cosmic rays is that they seem to come from all directions in space, indicating that they are generated by a variety of cosmic events and processes. Potential sources include supernova, which are powerful explosions that occur when massive stars reach the end of their life cycles. These explosions can eject particles with incredible force, transforming them into cosmic rays. Another possible source is active galactic nuclei, where supermassive black holes at the center of galaxies could be accelerating particles to extreme velocities through intense magnetic fields. Despite these theories, many cosmic rays exhibit energy levels that are difficult to explain through known astrophysical processes, suggesting that there might be more exotic or unknown sources at play. Some scientists even speculate that these particles could originate from beyond our galaxy, perhaps from events involving gamma-ray bursts or the collision of galaxy clusters. The study of cosmic rays is not just an academic pursuit, it has practical implications for life on Earth and human space exploration. When cosmic rays collide with the Earth's atmosphere, they create showers of secondary particles that can pose significant risks to astronauts and high-altitude flights. These particles can penetrate spacecraft and human tissue, potentially causing health issues such as radiation sickness and increasing the long-term risk of cancer. On a more positive note, cosmic rays have also played a role in advancing our understanding of fundamental physics. For instance, their interactions with the Earth's atmosphere have been crucial in discovering new particles such as the muon and understanding the nature of subatomic particles. The study of cosmic rays has led to significant advancements in particle physics, pushing the boundaries of what we know about the universe. The impact of cosmic rays on our planet extends to influencing climate and weather patterns. Some research suggests that cosmic rays may affect cloud formation by ionizing particles in the atmosphere, thereby impacting global climate systems. This potential link between cosmic rays and climate change is a subject of ongoing investigation and debate among scientists. Despite our progress in understanding cosmic rays, many questions remain unanswered. What are the precise sources of the highest energy cosmic rays? How are these particles accelerated to such incredible speeds? And what role do cosmic rays play in the broader context of the universe's evolution? As technology and observational techniques continue to improve, we hope to unveil more of the secrets that cosmic rays hold. In summary, cosmic rays are one of the most mysterious and fascinating phenomena in the universe. Their unknown origins, immense energy, and impact on space and Earth challenge our understanding of astrophysics and push us to explore the fundamental forces that shape our cosmos. The study of cosmic rays not only enriches our knowledge of the universe, but also holds practical implications for our daily lives and future space endeavors, ensuring that this cosmic enigma remains a compelling focus of scientific inquiry. The galactic center, the very heart of our Milky Way galaxy, is one of the most mysterious and dynamic regions in the cosmos. At the core of this enigmatic area lies Sagittarius A*, a supermassive black hole with a mass equivalent to about 4 million suns. Picture this colossal black hole as the anchor of our galaxy, exerting a powerful gravitational pull that influences the orbits of surrounding stars and gas clouds. The existence of Sagittarius A* presents several captivating questions about its origin, growth, and the role it plays in the evolution of the Milky Way. One of the biggest mysteries is how Sagittarius A* became so massive. Did it grow from the merger of smaller black holes, or did it rapidly accumulate mass by devouring nearby gas and stars? Observations suggest that black holes at the centers of galaxies like ours may grow intermittently, alternating between periods of intense feeding frenzies and relative dormancy. During active phases, the black hole can emit powerful jets of radiation and particles that can influence the entire galaxy, potentially regulating star formation and the distribution of interstellar matter. Scientists have also discovered that the galactic center is a bustling region filled with dense star clusters, clouds of molecular gas, and high-energy radiation. This makes it a perfect laboratory for studying extreme physical conditions and phenomena. Interestingly, it is also the site of mysterious objects known as G-objects, which appear to be gas clouds yet behave like stars. When these objects approach Sagittarius A*, they get stretched and heated by its tremendous gravity, emitting bright flares of infrared radiation. The nature of these G-objects remains unclear, sparking debates about whether they are stars cloaked in gas or entirely new classes of celestial bodies. Another fascinating feature of the galactic center is its high concentration of young, massive stars. This is unusual because the conditions near a supermassive black hole are typically too hostile for star formation. The intense gravitational forces and radiation should disrupt the accumulation of gas needed to form new stars. Yet there they are, shining brightly in the heart of our galaxy. This paradox raises questions about how these stars came to be. Are they the survivors of clusters that migrated inward from less hostile regions, or did they somehow form in situ despite the odds? One of the most significant recent discoveries concerning Sagittarius A* is the detection of rapid flares of X-ray light emanating from it. These flares occur when chunks of material, such as gas clouds or stars, get too close to the event horizon and are ripped apart by tidal forces. The resulting energy release produces bursts of X-rays, providing a rare glimpse into the behavior of matter in the extreme gravitational environment near a supermassive black hole. Researchers are also intrigued by the role Sagittarius A* plays in the broader dynamics of the Milky Way. For instance, it is believed that interactions between the black hole and surrounding matter could shape the spiral structure of our galaxy. Moreover, the galactic center's intense radiation environment has implications for the habitability of any nearby planets, influencing whether or not life could potentially exist there. As technology advances, astronomers are continually unveiling more about this mysterious region. Future missions and more powerful telescopes, such as the Event Horizon Telescope and the James Webb Space Telescope, promise to provide even more detailed observations of Sagittarius A* and its surroundings. By probing the galactic center, we hope to answer fundamental questions about the nature of supermassive black holes, the formation and evolution of galaxies, and the extreme conditions that govern the universe's most energetic phenomena. In summary, the galactic center and Sagittarius A* continue to be a focal point of astrophysical research, offering profound insights and posing new challenges that drive our quest to understand the cosmos. This enigmatic heart of our galaxy serves as a reminder of the incredible forces at play in the universe and the endless mysteries waiting to be uncovered. The next space mystery that has captured the imagination of scientists and stargazers alike is the hypothetical Planet 9. The concept of Planet 9 stems from observations of unusual orbital patterns in the Kuiper Belt, a distant region of our solar system filled with icy bodies and dwarf planets. These peculiar orbits suggest that a massive, unseen planet could be exerting a gravitational influence on these objects. But what exactly is Planet 9, and what evidence supports its existence? First proposed in 2016 by astronomers Konstantin Batygin and Mike Brown, Planet 9 is thought to be a giant planet, possibly 10 times the mass of Earth, orbiting far beyond Neptune. Unlike the well-known planets in our solar system, this mysterious planet would have an elongated, highly elliptical orbit, taking it hundreds or even thousands of years to complete a single trip around the Sun. This vast distance would make Planet 9 extremely difficult to detect with current telescopes, explaining why it has remained elusive. One of the key pieces of evidence for Planet 9's existence is the clustering of certain objects in the Kuiper Belt. These trans-Neptunian objects, or TNO, have orbits that are oddly aligned, suggesting they are being shepherded by the gravitational pull of a massive, unseen planet. Batygin and Brown's calculations show that the presence of a ninth planet could explain these orbital anomalies, providing a compelling case for its existence. Additionally, computer simulations support the idea that a planet of this size could maintain the observed clustering of TNOs over long periods. The potential discovery of Planet 9 would have profound implications for our understanding of the solar system. It would challenge our current models of planetary formation and migration, as well as offer insights into the early history of the solar system. If Planet 9 is found, it could help explain the dynamical evolution of our planetary neighborhood and the distribution of objects within it. Moreover, studying this distant world could reveal new information about the types of planets that exist in other star systems, shedding light on the diversity and complexity of planetary systems throughout the galaxy. Despite the tantalizing evidence, the search for Planet 9 is still ongoing. Astronomers are using some of the most powerful telescopes in the world, such as the Subaru telescope in Hawaii, to scan the sky for any signs of this elusive planet. The difficulty lies in its faintness and slow motion across the sky, making it a challenging target to identify. However, advancements in technology and observational techniques continue to improve our chances of finding it. The discovery of Planet 9 would be one of the most significant astronomical findings of our time, reshaping our understanding of the solar system and potentially leading to the discovery of even more distant objects and phenomena. Whether or not Planet 9 exists, the search itself is pushing the boundaries of our knowledge and demonstrating the relentless curiosity that drives scientific exploration. In summary, the mystery of Planet 9 remains one of the most captivating pursuits in modern astronomy. The evidence pointing to its existence challenges our understanding of the solar system and ignites our curiosity about the vast, uncharted regions beyond Neptune. As we continue our search for this hypothetical planet, we remain hopeful that one day we will uncover the secrets it holds, further expanding our knowledge of the cosmos. The extreme conditions on the surface of Venus make it one of the most mysterious and challenging places to study in our solar system. Venus, often called Earth's sister planet due to its similar size and composition, presents an environment that is anything but hospitable. The surface temperature of Venus is a staggering 900 degrees Fahrenheit, hot enough to melt lead. This intense heat is the result of a runaway greenhouse effect, where thick clouds of sulfuric acid trap heat from the sun, causing the surface to remain blisteringly hot. The atmosphere is composed mainly of carbon dioxide, with clouds of sulfuric acid, creating a pressure on the surface that is 92 times greater than Earth's, akin to being 900 meters underwater in the ocean. Imagine standing on Venus's surface. The sky would appear orange, and the air would be thick and oppressive. The landscape is dotted with volcanoes, vast lava plains, and deformed terrains known as tesserae, which resemble jumbled, rugged highlands. One of the greatest mysteries about Venus is its volcanic activity. While we know Venus has many volcanoes, it is unclear whether any are still active today. Some evidence, such as changes in sulfur dioxide levels in the atmosphere and hints of thermal anomalies, suggests there might still be active volcanism, but this remains unconfirmed due to the harsh conditions. Studying Venus is incredibly difficult because of these extreme conditions. Most spacecraft that have attempted to land on Venus have only survived for a few hours before succumbing to the intense heat and pressure. The Soviet Union's Venera program in the 1970s and 1980s managed to send several probes that landed on Venus, providing valuable data and the first images of its surface before they were destroyed by the hostile environment. These missions revealed a rocky, barren landscape strewn with boulders and covered in volcanic plains. Modern efforts to study Venus include orbiters like NASA's Magellan mission, which used radar to map the surface through the thick clouds, revealing detailed topography and geological features. However, our understanding is still limited, and new missions are being planned to further investigate this enigmatic planet. The upcoming NASA mission, Da Vinci Plus, aims to study Venus's atmosphere in detail, while Veritas will map the planet's surface with high resolution, hoping to unlock more of its secrets. The mysteries of Venus, from its extreme surface conditions to its volcanic activity, continue to challenge and intrigue scientists. Understanding Venus not only helps us learn about our neighboring planet, but also offers insights into the processes that can lead to such extreme greenhouse effects, which has implications for understanding climate change on Earth. As technology advances, we hope to one day send more robust landers that can endure Venus's harsh environment, allowing us to uncover even more about this fiery, enigmatic world. The next mind-blowing space mystery we are going to delve into is the methane on Mars. Methane spikes detected in the Martian atmosphere have generated significant excitement and curiosity among scientists, as they could potentially indicate the presence of life. Methane is a simple organic molecule that, on Earth, is predominantly produced by biological activities such as microbial processes in wetlands and the digestive systems of animals. However, methane can also be generated through geological processes such as serpentinization, where water interacts with certain types of rock. The first detection of methane on Mars was made by the European Space Agency's Mars Express spacecraft in 2004, followed by further measurements from NASA's Curiosity rover and Earth-based telescopes. These detections revealed episodic spikes of methane concentration in the Martian atmosphere, with levels fluctuating from background traces up to 10 times higher. This variability suggests that the source of methane might be localized and active, releasing the gas in sudden bursts. One of the most intriguing aspects of the Martian methane mystery is its potential implications for life. Methane's presence on Mars raises the tantalizing possibility that microbial life could exist or have existed on the planet, producing the gas as a metabolic byproduct. If microbial life is indeed the source, it would likely be located below the surface, where liquid water might still persist, protected from the harsh surface conditions. The discovery of subsurface life on Mars would be a groundbreaking revelation, profoundly impacting our understanding of life's potential to thrive beyond Earth. Alternatively, the methane spikes could be explained by geological processes. For instance, methane trapped in clathrates, which are ice-like structures, could be released during seasonal temperature changes or tectonic activity. Another possibility is that methane is produced through chemical reactions between water and olivine, a common mineral in Martian rocks. Both scenarios suggest that Mars has an active subsurface environment, which is geologically interesting even if it doesn't indicate biological activity. To pinpoint the source of Martian methane, scientists are employing advanced instruments and techniques. The ExoMars Trace Gas Orbiter, a joint mission by ESA and Roscosmos, is specifically designed to study trace gases in the Martian atmosphere, including methane. By analyzing the distribution and isotopic composition of methane, researchers hope to distinguish between biological and geological origins. Additionally, future missions like NASA's Perseverance rover aim to collect and analyze rock samples that could contain clues about ancient microbial life and methane sources. Understanding the mystery of Martian methane is crucial for our broader quest to explore the Red Planet. It informs our search for life and guides the selection of landing sites for future missions. The presence of methane also suggests that Mars remains an active planet with ongoing processes that could influence its habitability. In summary, the detection of methane on Mars is one of the most compelling puzzles in planetary science. Whether the methane originates from biological or geological sources, solving this mystery promises to enhance our knowledge of Mars and its potential to harbor life. As we continue to investigate this enigmatic gas, we edge closer to answering the profound question of whether we are alone in the universe. The Drake equation is one of the most fascinating tools in the search for extraterrestrial intelligence. Developed by astrophysicist Frank Drake in the 1960s, the equation attempts to estimate the number of advanced civilizations in our Milky Way galaxy that we might be able to communicate with. Imagine a mathematical formula that breaks down the seemingly insurmountable question of, are we alone in the universe, into a series of more manageable, measurable terms. The equation itself reads, n equals r asterisk times fb times n times fl times phi times fc times l. Each of these variables represents a different factor that could influence the number of detectable civilizations. R asterisk is the average rate of star formation in our galaxy. Stars are the birthplaces of planets, so understanding how frequently they form gives us the first clue in our search. Next, FP represents the fraction of those stars that have planetary systems. With recent advancements in exoplanet discoveries, we've found that planets might be more common than we once thought. Then, Ni is the number of planets in each system that could potentially support life, residing in the so-called habitable zone where conditions might be just right for liquid water. Moving further, FL is the fraction of those potentially habitable planets where life actually arises. This term is particularly enigmatic because so far, Earth is the only place we know of that harbors life. Next, Phi represents the fraction of planets with life that evolves into intelligent beings capable of developing technology. This is where the equation delves into the mysteries of evolution and whether intelligence is a rare or common outcome. Following that, FC is the fraction of civilizations that develop technologies that release detectable signs into space, like radio waves. Lastly, L is the length of time these civilizations emit signals into space for us to detect. The Drake equation is not just about the numbers, it encapsulates the enormous uncertainties and wonder regarding our place in the universe. Each variable in the equation is a mystery unto itself, fraught with scientific and philosophical questions that challenge our understanding. For instance, we still don't know how often life transitions from simple organisms to complex, intelligent beings, or how long civilizations can survive without self-destructing. Moreover, the equation opens up discussions about the possible reasons we haven't detected any signals yet, touching on themes like the Fermi paradox and the Great Filter hypothesis. As we improve our technology and expand our knowledge, we continue to refine the estimates for each term in the Drake equation. Projects like the Kepler Space Telescope and the upcoming James Webb Space Telescope aim to discover more exoplanets and assess their habitability. Meanwhile, initiatives like SETI, the search for extraterrestrial intelligence, scour the skies for any signs of alien civilizations. Every new discovery, whether it's the detection of a new exoplanet or understanding more about life's origins on Earth, brings us a step closer to solving the cosmic puzzle posed by the Drake equation. In summary, the Drake equation serves as a framework that guides our quest to estimate the number of advanced civilizations in the Milky Way. It highlights the mysteries of star formation, planet habitability, the emergence of life, and the development of technology. While the equation itself doesn't provide concrete answers, it invites us to explore the vast and intriguing unknowns of the cosmos. The Oort cloud is one of the most fascinating and least understood regions of our solar system. Imagine a vast spherical shell of icy bodies surrounding the Sun at a distance that stretches nearly a light year away. This distant region, named after Dutch astronomer Jan Oort, is thought to be the source of long-period comets that occasionally visit the inner solar system, showing off their spectacular tails as they approach the Sun. But what exactly is the Oort cloud, and what mysteries does it hold? The Oort cloud is believed to be a remnant from the early solar system, made up of countless icy objects that formed closer to the Sun before being flung outward by gravitational interactions with the giant planets. These objects are composed mainly of water, methane, ammonia, and other volatile compounds that can evaporate easily. This makes the Oort cloud an invaluable time capsule, preserving material from the dawn of our solar system and potentially offering clues about its formation and evolution. One of the greatest mysteries surrounding the Oort cloud is its sheer size and boundary. While it is theorized to extend from about 2,000 to 100,000 astronomical units from the Sun, its vast distance makes direct observation incredibly challenging. Most of what we know about the Oort cloud comes from studying the trajectories of long-period comets as they swoop into the inner solar system. These comets provide indirect evidence of the Oort cloud's existence and hint at its immense scale, but many details remain elusive. Another intriguing question is how the objects in the Oort cloud remain stable over such vast timescales. Given the gravitational influences of passing stars and the Milky Way itself, one might expect these bodies to be perturbed or ejected more frequently. However, the Oort cloud appears to be a relatively stable reservoir, occasionally releasing comets that are nudged toward the inner solar system by these distant gravitational interactions. This stability suggests complex gravitational dynamics at play, which scientists are still striving to understand fully. The potential origin of the Oort cloud also presents a captivating puzzle. While some theories suggest it was formed from the leftover building blocks of the solar system, others propose that it could contain objects captured from other star systems during close encounters in the Sun's past. If true, this would mean the Oort cloud holds a mixture of materials from different parts of our galaxy, offering a unique opportunity to study the diversity of planetary systems. Furthermore, the Oort cloud raises questions about the frequency and impact of cometary bombardment on Earth and other planets. Long-period comets from the Oort cloud could have played a significant role in delivering water and organic materials to Earth, potentially influencing the development of life. Conversely, these comets also pose a threat, as their unpredictable paths make them challenging to detect and track, raising concerns about potential future impacts. In summary, the Oort cloud is a distant, enigmatic region that serves as a reservoir for long-period comets and a time capsule from the early solar system. Its vast size, mysterious stability, and potential origins from both our own and other star systems make it a key area of interest for astronomers. As our observational techniques and technologies advance, we hope to unlock more of the secrets hidden in this remote and icy frontier, furthering our understanding of the solar system's formation and the broader cosmic environment. The next powerful and mysterious phenomena we need to explore are gamma-ray bursts. Gamma-ray bursts, or GRB, are the most energetic events known to occur in the universe, releasing more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. These bursts are so powerful that, despite occurring billions of light-years away, they can outshine entire galaxies for a brief moment. The mystery of GRBs lies in their origins and the mechanisms that produce such intense explosions. Gamma-ray bursts are typically classified into two categories: long-duration and short-duration bursts. Long-duration GRBs last from a few seconds to several minutes and are believed to be associated with the deaths of massive stars. When a massive star exhausts its nuclear fuel, its core collapses into a black hole or neutron star, resulting in a supernova explosion. This collapse can form an accretion disk around the new black hole, which then funnels material into powerful jets that travel at nearly the speed of light. These jets produce the gamma rays we detect as a burst when they are pointed directly at Earth. Short-duration GRBs, on the other hand, last less than 2 seconds and are thought to originate from the merger of compact objects, such as binary neutron stars or a neutron star and a black hole. These mergers produce gravitational waves and result in a kilonova explosion, releasing gamma rays in the process. The detection of both gamma rays and gravitational waves from a single event in 2017 provided strong evidence for this theory, marking a significant advancement in our understanding of these cosmic phenomena. One of the most intriguing aspects of gamma-ray bursts is their afterglow. After the initial burst, GRBs emit a fading afterglow of X-rays, optical light, and radio waves which can last from hours to weeks. Observing this afterglow allows scientists to study the environment around the burst and gain insights into the properties of the progenitor system. For instance, the afterglow can reveal the density of the surrounding material, the magnetic field strength, and the energy of the explosion. Another mystery surrounding GRBs is their distribution across the sky. They appear to come from random directions, suggesting that they occur in galaxies throughout the universe. This isotropic distribution implies that GRBs are linked to events that can happen in any type of galaxy, whether it's a small, dwarf galaxy or a massive spiral galaxy like our own Milky Way. Despite significant progress, many questions about gamma-ray bursts remain unanswered. For example, the exact conditions required to produce the powerful jets observed in long-duration GRBs are still not fully understood. Additionally, the role of magnetic fields in the formation and collimation of these jets is an area of active research. For short-duration GRBs, determining the precise nature of the progenitor systems and the frequency of such mergers in the universe continues to be a challenge. The study of gamma-ray bursts not only helps us understand these extraordinary events, but also sheds light on other areas of astrophysics. For instance, GRBs can serve as probes for studying the early universe. Since they are visible at great distances, they provide information about the conditions of the universe when it was only a fraction of its current age. Additionally, the detection of elements produced in kilonova explosions helps us understand the origin of heavy elements like gold and platinum in the universe. In summary, gamma-ray bursts are among the most powerful and enigmatic phenomena in the cosmos, with origins linked to the deaths of massive stars and the mergers of compact objects. Studying GABs provides valuable insights into the extreme physics involved in these events and their role in the broader cosmic landscape. As our observational capabilities continue to improve, we look forward to uncovering more about these incredible bursts of energy and the mysteries they hold within. The next captivating region of space we need to explore is the Kuiper Belt. Imagine a vast, icy expanse located beyond the orbit of Neptune, filled with billions of small icy bodies and dwarf planets. This region, known as the Kuiper Belt, is significant due to its role in understanding the formation and evolution of our solar system. Discovered in 1992, the Kuiper Belt stretches from approximately 30 to 55 astronomical units from the Sun, encompassing a range of celestial objects that provide a glimpse into the primordial conditions of the early solar system. Among these objects are some of the most well-known and intriguing bodies, such as Pluto and Eris. Pluto, once considered the 9th planet of our solar system, was reclassified as a dwarf planet in 2006. Its demotion highlighted the need to re-evaluate our definitions of planets and sparked renewed interest in studying Kuiper Belt objects or KBOs. Pluto's surface is covered with nitrogen, methane, and carbon monoxide ices, and it possesses a thin atmosphere that undergoes seasonal changes as it orbits the Sun. One of the most striking features of Pluto is its heart-shaped region known as Tombaugh Regio, which showcases a variety of geological features, including mountains made of water ice and plains of frozen nitrogen. The New Horizons mission, which flew by Pluto in 2015, revealed these and many other details, providing unprecedented insights into this distant world. Eris, another dwarf planet in the Kuiper Belt, was discovered in 2005 and is slightly smaller than Pluto but more massive. Eris's discovery was a key factor in the reclassification of Pluto and has since become a focal point for understanding the diversity of objects within the Kuiper Belt. Eris has a highly elliptical orbit, taking it much farther from the Sun at times, and its surface is covered in a layer of methane ice, giving it a bright, reflective appearance. Studying Eris and other similar objects helps scientists understand the composition and dynamics of the outer solar system. Beyond Pluto and Eris, the Kuiper Belt is home to a multitude of other fascinating objects, each with its own unique characteristics. These KBOs range in size from small rocky bodies to large dwarf planets, and their diverse compositions suggest a complex history of formation and evolution. Some KBOs, like Haumea and Makemake, have unusual shapes and rapid rotation rates, raising questions about their internal structure and collisional history. One of the greatest mysteries of the Kuiper Belt is its role in the broader context of planetary science. The icy bodies within this region are thought to be remnants from the early solar system, preserved in a relatively unaltered state. By studying these objects, scientists hope to gain insights into the processes that led to the formation of the planets and the distribution of volatile materials, such as water, throughout the solar system. Additionally, the Kuiper Belt is believed to be the source of short-period comets, which have orbits that bring them into the inner solar system. These comets are thought to originate from the scattering and gravitational interactions within the Kuiper Belt, providing a direct link between this distant region and the more dynamic inner solar system. The Kuiper Belt also poses intriguing questions about the potential presence of additional undiscovered planets. Some astronomers have hypothesized the existence of a hypothetical planet 9, a massive object that could be influencing the orbits of KBOs. While direct evidence for such a planet remains elusive, ongoing observations and studies continue to explore this tantalizing possibility. In summary, the Kuiper Belt is a treasure trove of icy bodies and dwarf planets that hold clues to the early solar system's formation and evolution. Its significance lies in the diverse range of objects it contains, from the well-known Pluto and Eris to the multitude of smaller KBOs. As we continue to explore and study this distant region, we open new windows into understanding the origins and dynamics of our solar system, further expanding our knowledge of the cosmos. The next perplexing mystery we are going to investigate is the Pioneer Anomaly. The Pioneer Anomaly refers to the unexplained deviations in the trajectories of the Pioneer 10 and 11 spacecraft. Launched in the early 70s, these spacecraft were on missions to explore the outer planets and eventually head into interstellar space. However, as they traveled farther from the Sun, scientists noticed a tiny but consistent acceleration toward the Sun that could not be explained by the known forces acting on them. The anomaly was first detected in the early 80s when precise tracking data revealed that both spacecraft were slowing down more than expected. This unexpected deceleration puzzled scientists and led to extensive analyses and debates. Various hypotheses were proposed to explain the Pioneer Anomaly, ranging from mundane possibilities like gas leaks from the spacecraft to more exotic theories involving modifications to our understanding of gravity. One of the initial theories was that heat emitted from the spacecraft's power sources or instruments could be creating a small thrust, causing the observed deviations. The radioactive decay of plutonium in the spacecraft's thermoelectric power sources generates heat, and if this heat is radiated asymmetrically, it could cause a tiny force in the opposite direction. Detailed thermal models of the spacecraft were created to see if this could account for the anomaly, but it remained unclear if heat dissipation alone was sufficient to explain the observed acceleration. Another theory suggested that the anomaly might be due to the gravitational attraction of massive objects in the Kuiper Belt or Oort cloud. If there were large, undiscovered celestial bodies exerting gravitational forces on the spacecraft, it could potentially account for the deviations. However, this theory faced challenges as it would require a significant amount of mass distributed in a very specific way, which was not supported by other observations. The most intriguing possibility was that the Pioneer Anomaly might indicate new physics beyond our current understanding of gravity. Some scientists speculated that it could be evidence for modifications to Newtonian gravity or general relativity, possibly hinting at new forces or particles. This idea generated considerable excitement as it opened the door to the possibility of discovering fundamental aspects of the universe that were previously unknown. To solve this mystery, scientists undertook a comprehensive review of the tracking data, spacecraft design, and environmental factors. Advances in data analysis techniques and better models of thermal radiation helped refine the understanding of the forces acting on the spacecraft. In 2012, a detailed study concluded that the anisotropic emission of thermal radiation from the Pioneer spacecraft could account for most, if not all, of the observed anomalies. This explanation suggests that the small thrust generated by heat radiating from the spacecraft's components was sufficient to cause the deviations in their trajectories. While the resolution of the Pioneer anomaly did not lead to new physics, it highlighted the importance of thorough analysis and the need for precise measurements in space exploration. It also underscored the potential for even small, seemingly insignificant forces to have measurable effects over vast distances. The investigation into the Pioneer anomaly has contributed to our understanding of spacecraft navigation and the challenges of deep space missions. In summary, the Pioneer anomaly represents a fascinating chapter in space exploration, where unexplained deviations in spacecraft trajectories led to rigorous scientific inquiry and debate. The resolution of the anomaly through detailed analysis of thermal radiation has enhanced our understanding of the forces at play in space and demonstrated the complexities of accurately navigating spacecraft in the vast expanse of the cosmos. As we continue to send missions beyond our solar system, the lessons learned from the Pioneer anomaly will inform future endeavors and help us better comprehend the intricate dynamics of space travel. The missing baryons problem presents one of the most puzzling mysteries in cosmology. In simple terms, baryons are particles like protons and neutrons that make up ordinary matter. When we look at the universe, we can only account for about half of the baryonic matter predicted by theoretical models. So where are these missing baryons? This discrepancy has puzzled astronomers and physicists for decades, leading to numerous investigations and theories to solve this cosmic riddle. One promising area of research focuses on the warm-hot intergalactic medium, or WIM. This is a diffuse, web-like structure of hot gas that stretches between galaxies and could potentially house these missing baryons. Observations using space telescopes, such as the Chandra X-ray Observatory and the Hubble Space Telescope, provide indirect evidence that WIM might indeed contain a significant fraction of the missing matter. These telescopes detect the absorption and emission lines of highly ionized elements like oxygen in the X-ray spectrum, which suggests the presence of this elusive gas. Another intriguing avenue involves studying the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang and provides a snapshot of the early universe. By analyzing its fluctuations, scientists develop detailed models of how matter should be distributed. But reconciling these models with current observations remains challenging, fueling the mystery of the missing baryons. Fast radio bursts, or FRBs, have recently emerged as a novel tool in this search. FRBs are brief, intense bursts of radio waves from distant galaxies. When these signals travel through space, they encounter different materials, including the WIM, and get slightly scattered and delayed. By studying these delays, scientists can infer the density of intervening baryons, offering a new method to map the missing matter. Another method involves studying the distribution and movement of galaxies. By examining the gravitational influences exerted by visible matter, astronomers hope to uncover hidden baryons affecting these dynamics. This approach complements direct observations, providing a broader picture of where the missing baryons might be located. Computer simulations using advanced algorithms also play a crucial role in this quest. These simulations model the evolution of the universe from the Big Bang to the present, tracking the movement and interaction of baryonic matter. Comparing these simulations with actual observations helps identify discrepancies and potential locations of the missing baryons. The missing baryons problem challenges our understanding of the universe's mass and structure, driving innovation in observational techniques and theoretical models. As we continue to explore and refine our methods, we anticipate that solving this mystery will not only fill in gaps in our knowledge, but also enhance our comprehension of cosmic evolution and the large-scale structure of the universe. In summary, the missing baryons problem highlights a significant gap in our understanding of cosmic matter. Through innovative observational techniques, advanced simulations, and the continued study of cosmic phenomena, scientists are determined to locate this elusive matter, bringing us closer to unraveling the full story of the universe's composition. The next awe-inspiring mystery we are going to explore is the concept of the multiverse. Imagine countless parallel universes existing alongside our own, each with its own unique set of physical laws, constants, and histories. This idea, known as the multiverse theory, posits that our universe is just one of many, possibly infinite, universes that together comprise all of existence. The multiverse concept challenges our understanding of reality, pushing the boundaries of physics and cosmology. One of the main motivations for the multiverse theory comes from the field of cosmology. According to the inflationary model of the Big Bang, our universe underwent a rapid expansion in its first moments. Some versions of this model suggest that inflation could occur in different regions of space at different times, creating pocket universes with varying properties. This idea, known as eternal inflation, leads to a multiverse where each bubble universe may have its own distinct physical constants and laws of nature. Another compelling argument for the multiverse arises from string theory, a theoretical framework that attempts to reconcile general relativity and quantum mechanics. String theory posits the existence of multiple dimensions beyond the familiar three spatial dimensions and one time dimension. These extra dimensions could be compactified or curled up in various ways, resulting in a vast number of possible universes, each with its own unique configuration of dimensions and physical properties. Quantum mechanics also hints at the possibility of parallel universes. The many worlds interpretation of quantum mechanics suggests that every time a quantum event occurs with multiple possible outcomes, all outcomes are realized in separate, branching universes. For example, in one universe, you might choose to go left, while in another universe, you go right. These branching universes continually diverge, leading to an ever-growing multiverse of possibilities. The concept of the multiverse also raises profound philosophical and existential questions. If multiple universes exist, each with different histories and outcomes, what does that mean for our sense of individuality and identity? Are there versions of ourselves living different lives in parallel universes? These questions challenge our perception of reality and our place within the cosmos. While the multiverse theory is intriguing, it also presents significant challenges for scientific inquiry. One of the primary difficulties is the lack of direct observational evidence. Testing the existence of other universes is currently beyond our technological capabilities, and some argue that the multiverse theory is inherently untestable and therefore not a scientific hypothesis. However, proponents of the multiverse argue that certain indirect evidence and mathematical consistency can lend support to the theory. For instance, some aspects of our universe, such as the fine-tuning of physical constants that allow for the existence of life, might be explained by the multiverse. If there are countless universes with varying properties, it is not surprising that at least one would have the right conditions for life to emerge. This anthropic principle suggests that our universe's seemingly special properties are simply a result of being in a universe where observers like us can exist. As we continue to study the cosmos and develop new theories, the concept of the multiverse remains a topic of intense debate and fascination. It challenges our understanding of reality, pushing us to reconsider the nature of existence and the limits of scientific exploration. In summary, the multiverse theory presents the mind-bending idea of parallel universes, each with its own unique properties and histories. Whether arising from cosmology, string theory, or quantum mechanics, the concept of the multiverse expands our understanding of reality and raises profound questions about our place in the cosmos. As we explore this captivating idea, we are reminded of the vast and mysterious nature of the universe and the endless possibilities that lie beyond our current understanding. In summary, we've explored a plethora of the universe's most captivating enigmas, from the mind-bending mysteries of black holes and the elusive nature of dark matter to the extreme environments of neutron stars and the enigmatic fast radio bursts. Our journey through space has showcased just how little we truly understand about the cosmos. We delved into the gravitational pull of the Great Attractor and the perplexing force of dark energy, along with the thought-provoking Fermi paradox that questions why we haven't encountered extraterrestrial intelligence despite the vast number of stars and planets. The wonders of exoplanets revealed the diverse and extreme conditions possible on other worlds, while the WOW signal and cosmic rays showcased the mysterious signals and particles that travel across the universe. We unraveled the dynamic heart of our galaxy at the galactic center, speculated on the hypothetical planet 9, and explored the intense surface conditions of Venus. The Martian methane spikes hinted at the potential for life on Mars, and the Drake equation provided a framework for estimating the number of advanced civilizations in our galaxy. We ventured into the distant Oort cloud and the powerful gamma-ray bursts that illuminate the farthest reaches of space. The Kuiper belt offered insights into the early solar system, while the Pioneer anomaly highlighted the complexities of deep space navigation. The missing baryons problem challenged our understanding of cosmic matter, and the multiverse theory expanded our perception of reality, suggesting the existence of countless parallel universes. Each of these mysteries pushes the boundaries of our knowledge, urging us to keep exploring and questioning the universe around us. As you ponder these cosmic enigmas, we invite you to join us on this journey of discovery. Subscribe to our channel for more mind-blowing content that delves into the wonders of space, the mysteries of the universe, and the endless possibilities that await us in the cosmos. Don't forget to like this video and hit the notification bell so you never miss an update. The universe is vast and full of secrets, and together we'll continue to uncover them one mystery at a time.